Now, Poincare invariants work also for any sort of canonical variables. As long as you have a pair of canonical variables, say we can pass from QP to other variables, say theta j, which are our angle action variables, then these variables are also Poincare invariant. That means that we can define another quantity j prime, and let's call that the integral of the omega dj, where this angle theta increases from 0 to 2 pi. And now we can make use of Green's theorem. If the area integral of dx dy is equal to the closed path integral of x dy, then the integral of d theta dj is equal to the integral in the closed path of j in d theta. And because the action j was a constant of motion, this is then just j, because you can take this j out of the integral, and theta will integrate to 2 pi. So this becomes simply j. And again, because these variables are canonical, you can replace j and theta by p and q. Therefore, your result is that j is equal to 1 over 2 pi times the line integral of p dq. So this is the action j related to canonical coordinates q and p. Now let's find out how we find the angle theta. For that, we're going to consider the Hamilton-Jacobi equation. The Hamilton-Jacobi equation depends on the definition of a generation function. Imagine that you have 2 points in space, the point w node and another point w. And you have 2 distinct paths going from w0 to w. Say that you can do this path, that would be the path gamma 0, or you can also have this other path here, the path is gamma 1. So let the full path going from w0 to w through gamma 0, and then back for the negative of gamma 1, let this path be the path gamma. Now, if you have 2 sets of canonical coordinates, q and p, and q prime and p prime, then by conservation of the Poincare invariant, then the closed path integral on the path gamma of dq p minus dq prime p is equal to 0. Then the closed path integral of p dq is integral to the closed path integral of p prime in dq prime. That means that we can subtract the right-hand side from both sides and write it as a single integral. The closed path integral of p dq minus p prime dq prime is equal to 0. Now the path gamma is the path gamma 0 minus the path gamma 1. That means that we can split this integral into an integral through the path gamma 0 minus the integral through the path gamma 1, minus because the gamma 1 is the reverse of the path gamma on the upper part of this diagram, and this is equal to 0. Therefore, you can sum the second integral on both sides, and this is what you have. The integral in gamma 0 of p dq minus p prime dq prime is equal to the integral over the path gamma 1 of p dq minus p prime q prime. So the integrand is the same on both sides. It's only the path that is changing. So it doesn't matter if you take the path gamma 0 or the path gamma 1 to go from w0 to w, the result's the same. That means that this integral does not depend on the path. So for any fixed initial point w0 and final point w, we can write that this integral is always going to result in the same function. Call this function s of the point w. So we can take the derivative on both sides and define it in the differential ds, which is then equal to the integrand. So thus, ds is a exact differential, and s is called the generation function. It is the generating function of the canonical transformation from the variables qp to the variables q prime and p prime. Now, since ds is an exact differential, you can take the derivative of this with respect to q, and that then becomes p is equal to ds dq. So if we go back to the Hamilton equation, where the Hamiltonian, which is a function of q and p, is equal to the energy, and we substitute what we just found for p as given by the generation function, then we eliminate p from the Hamiltonian. substitute P for the derivative of the generation function over Q, and that is equal to the energy. This result is the Hamilton-Jacobi equation. And one of its advantages over the Hamilton equation is that instead of having 6 variables, 3 for Q and 3 for P, you have only 4 variables, 3 for the position and 1 the generation function. And because of that, this equation is easier to solve. We can immediately see how we get the action. If we write that the action J is equal to the path integral of P dq over the path gamma, and substitute now P as given by the generating function, then this equation becomes, which is trivial to solve, because the dq's here cancel, and this is simply the increment in the generating function. So we found how to find the action. The action J, which is an integral motion, is simply the increment of the generating function as you go through the path gamma. So let's see how this process works in a simple example. In the next video, let's solve the harmonic oscillator.